next thing I want to talk about is turning points. If f is a polynomial of degree n, then the graph has at most n minus 1 turning points. Turning points are where my graph changes from decreasing to increasing or increasing to decreasing rate of change. Woo! If the graph of a polynomial has at least n minus 1 turning points, then the degree of f is at least n. Notice it's at most and at least. It could have less than n minus 1 turning points, and that would be okay too. So the number of turning points on this graph are 1, 2, 3. Note, this is not a turning point, it's a 0. So our minimum possible degree could be, so our minimum possible degree n would be 4. The end behavior of a polynomial is the same as that of its power function. Remember, polynomials with even degree head the same direction. If I've got a negative leading coefficient, they're flipped upside down. If I have a polynomial of odd degree, right, it's doing kind of like the walk like an Egyptian. Remember the Bangles from the 80s? No, just me. Okay, so its end behavior goes in opposite directions. So here are end behaviors. So here I have an even polynomial, and I have that because my leading coefficient is greater than 0, my end behavior heads in the same direction, and it heads in the positive direction, positive I direction. If I have a less than 0a, it's going to head in the negative direction. If my a is positive and my degree is odd, it rises from left to right. Right? It goes down and then it goes up. And the opposite is true if my degree is less than 1. It goes from right to left. It's the opposite. From top to bottom, bottom to top, I guess. Here are end behavior of our function, and the end behavior of our function tells us our limits, right? If my function's even, the leading coefficient's positive. As x approaches positive infinity or negative infinity, my y value approaches infinity. The same is, oh, there's some gaps. If my function is even and the leading coefficient is negative, as x approaches positive infinity or negative infinity, my function approaches negative infinity. As I'm odd and my leading coefficient is positive, as x approaches positive infinity, my graph approaches positive infinity. And as my x approaches negative infinity, my graph approaches negative infinity. My y values approach negative infinity. If I have an odd function and the leading coefficient is negative, again, it goes from bottom to top. So if my graph approaches positive infinity, it goes to negative infinity via y. And as my x approaches negative infinity, my graph goes to positive infinity for the y value. Remember that y is f of x. And we discussed those in class as limits. Limits are a concept you're going to talk quite a lot about in calculus for those of you taking calc. So what are the limits of f of x as x goes to negative infinity and positive infinity? So as this function heads towards, as x goes to negative infinity, this graph goes to positive infinity. And as x goes to positive infinity, this graph also goes to positive infinity. Let's take a look over here. So I have as x goes to negative infinity, my y values also go to negative infinity. And I have as x goes to positive infinity, my y values also go towards positive infinity. So as x gets bigger, y gets bigger. Over here, as x gets smaller, y gets smaller. Next, I want us to talk about analyzing the graphs of functions. So given a polynomial function, there's so much that we can learn from our polynomial. So we can tell that its degree is the largest degree on x, and that'll tell me a lot about its end behavior. We know its y-intercept is f of 0 equals a naught, so its y-intercepts are constant. Our graph is smooth and continuous. Oh, I didn't even mention that its domain is all real numbers. That n can also tell us the maximum number of turning points, which is n minus 1. If our graph has a 0 of even multiplicity, it touches the x-axis. If we have a 0 of odd multiplicity, it crosses the x-axis. Between zeros, my graph is either always above or below the x-axis, and my end behavior of my graph behaves a lot like the power function associated with its leading term. So, steps to analyzing a function. Let's determine its end behavior. We want to find our x and y intercepts. We want to determine the zeros, and we're going to use that to determine if our graph crosses or touches the x. We can determine a maximum number of turning points and then sketch a graph of the function to the right. So here I have f of x equals 2x minus 1 times x minus 3 squared. Well, I don't know what degree this is. I probably should FOIL this out. So I have 2x minus 1 times x squared minus 6x plus 9. When we FOIL this out, we don't just distribute that negative. So I have f of x equals 2x cubed minus 12x squared plus 18x minus x squared plus 6x minus 9. We should probably simplify this bad boy. So I have f of x equals 2x cubed minus 13x squared plus 24x minus 9. So my end behavior, because it's an odd degree and it has a positive leading coefficient, my end behavior is going to be like this. Find the x and y intercepts. Well, my y-intercept is f of 0, which is negative 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my y-intercept. My x-intercepts are both of those set equal to 0. I have 2x minus 1 equals 0, so that means x equals a half. And I have x minus 3 equals 0, so x equals 3. And this has a multiplicity of 2. That means my graph is just going to touch the x-axis versus cross. So I have an x value at 1/2 and at 3, 3. My maximum number of turning points is going to be our degree minus 1, which is 2. So I can kind of sketch a graph of our function like so. Beautiful. What a cute function. And this is what our graph should look like if you graphed it in Desmos, just so we could check our answers. What if I want to find a polynomial that meets given criteria? So I want to find a polynomial whose zeros are -7, 2, and 3. Well, I don't know what my leading term's gonna be, but my real zeros, remember that if I have x equals -7, if I move that over, it becomes x plus 7, so you have to flip the sign. So I have x plus 7, x minus 2, x minus 3. Then we would FOIL this bad boy out. So I have a times x plus 7, x squared minus 5x plus 6, f of x equals a, times x cubed minus 5x squared plus 6x minus plus 7x squared minus 35x plus 42. So f of x equals a times x cubed plus 2x squared, 6x and -35x give me a -29x plus 42. And any leading coefficient, positive or negative, would have these same zeros. So if I wanted to find a polynomial whose real zeros were -7, 2, and 3, and had a leading coefficient of 1, it would just be f of x equals x cubed plus 2x squared minus 29x plus 42. What I did in class was I showed you this brief little video where as we change the coefficient of our function, our zeros never change, but the shape of our graph does a little bit. So I wanted you guys to be able to see that. I thought it was pretty cool, and I made this in Desmos. What if I want to find a polynomial with real zeros 1, 2, and 4 that passes through a specific point? So I have f of x equals some leading coefficient times x minus 1, x minus 2, x minus 4. Remember because it was x is 1 to move it over, the sign changes. So I have f of x equals a, x minus 1 times x squared minus 6x plus 8. F of x equals a times x cubed minus 6x squared plus 8x minus x squared plus 6x minus 8. So I have f of x equals a times x cubed minus 7x squared plus 14x minus 8. And now I have some information. I know that when x is 0, y is 4. So I can solve for my a. I would have 4, so that's y, equals a times 0 cubed minus 7 squared plus 14 times 0 minus 8. That's an infinity symbol, but I meant for it to be an 8. So I have 4 equals a times negative 8. Divide both sides by negative 8. I get that my leading coefficient can be 1/2. So to meet the criteria of being a polynomial with these three real zeros that passes through this point, my leading term would be negative 1/2. So I would have f of x equals negative 1/2 x cubed plus 7 halves x squared minus 7x minus plus 4. This would be our polynomial. We can also find a polynomial from a graph. But here's the thing. We don't really know what degree is, right? This is going to be an even degree. This is going to be an odd degree, right? So we could find a particular polynomial, but I don't know the degree. Even though I know the the y-intercept, it's a little bit trickier. But let's just assume that we only have degree 1 and 2 terms. So I'd have f of x equals x plus 3 times x minus 5 times x minus 2 squared for some a. So I have f of x equals a, x plus 3, x minus 5. This didn't take up so much space. X squared minus 4x plus 4. F of x equals a, x plus 3 times x cubed minus 4x squared plus 4x minus 5x squared plus 20x minus 20. F of x equals a, it's better work, x cubed minus 9x squared plus 24x minus 20. Then we distribute again. So much distribution.